Hello everyone, in this video I'm going to analyze a frame using flexibility method. So let's take an example having one end as fixed, another end as here this we have a roller support. Let's take a point load of 15 kilonewton and this length 3 meter, 2 meter and this height as 6 meter. And let's name this as A, B, C. Okay. So in order to analyze this indeterminate structure, if you can see here, we have here 3 reaction and here 1 4. So 4 minus 3 1. So the degree of indeterminacy is 1. So in order to solve this indeterminate structure, we are going to divide this into two parts. Two structure like primary structure. Okay, so you can see this is here. Let's take with load 15 kilonewton. This is our primary structure and a secondary structure. Then we'll be analyzing this. In secondary structure there is no load and the support C here we are going to take it as reaction at C, of C. Okay, so this is our secondary structure. So we'll be analyzing now both. You can see both are now determinate structure. We'll be analyzing this using virtual force method. As you know that virtual force method can be used only for determinate structure. In previous videos I've already solved many problems, examples I've solved using virtual force method. And also one beam we have analyzed using flexibility method. So here we are going to solve or analyze this frame member. So first step is divide into two determinate structure. You can see primary and secondary. Primary we are having a load, but we have removed this one redundant support. We can say degree of, so this support C we have removed in primary structure, whereas in secondary structure we have taken this reaction as RC. Now we'll be solving independently both using virtual force method. Then we will use a compatibility condition, compatibility equation to solve this. So primary structure we are going to use virtual force method in order to analyze this primary structure. So let's take the deflection at C for the primary structure. So I'm taking P for primary structure, deflection at C. This is equal to, we are going to integrate this with real moment plus virtual moment. So if you look at for the primary structure, so this is 15 kilonewton. Okay, so the moment, real moment I'm going to calculate, and for the same if there is a virtual force at end C, because we are calculating the deflection at C, that's why here I'm going to put a virtual force unit force as 1. So this I'm going to calculate the virtual moment. So let's consider here at any section Z, okay, which is from here. So your moment will be 15 multiplied by this distance. So this distance will be total Z minus, this is 2 meter. You can see in the question it's given 2 meter. So Z minus 2. So same here, if I take a section at distance Z, the moment is 1 multiplied by Z, so it is Z. So integrating this, the real moment is 15 multiplied by Z minus 2 by EI we take, multiplied by the Z, the virtual moment, dz, and this integration is from, if you look at here, from 0 to 2 there is no force, okay, there is no force, there is no movement, that's why. So here will not integrate for this portion, will integrate from here. So Z varies from 2 to here it is 5 meter, because this is 3 meter, this is 2 meter, so total is 5. So the integration will go from 2 to 5. Okay, then this plus, then you can see there is this B A part, so which is 6 meter, so 0 to 6. So what will be the moment here? So the moment here, you can see that here 15 is the force, so 15 multiplied by this 3 is 45. So this here, the moment is 45 kilonewton meter. So 45 by EI. So if you look at the virtual force method, you can that video, if you watch, you can understand more about virtual force method. So we are applying that method here, so where the integration we do with moment for the real structure with a virtual force we apply, and we multiply with the virtual. So you can see here, this is the virtual moment. So here this is 1 multiplied by total 5 meter, so 5 kilonewton meter for this BA. So 5 dz, and this dz is from 0 to 6. So we are going to calculate this. So this will be 15, if I open this bracket, this will be 15 z square minus 30z, integrating 2 to 5 dz, plus this is 225 dz. So 1 by EI I am just taking outside for both the integral. This is from 0 to 6. Okay, so 1 by EI, 15z square means 15z cube by 3 minus 30z square by 2, 0, this is 2 to 5 plus 225z, 0 to 6. So this, if I calculate, I am getting 270 by EI plus this 225 multiplied by 6, which gives 1350 by EI. So total is 1620 by EI. So this is for the deflection at sea due to the primary structure. Now similarly we will be analyzing for the secondary structure. Okay, for this, the secondary structure, similarly we have this virtual movement. So this was for primary. Now coming to the secondary, we have this RC, and virtual moment when we apply, same, delta P equal to 1. Okay, so here delta C, same, deflection at C due to the secondary structure, so S I will put. This is equal to, so I'm going to multiply. So this, you can see the real moment will be RC into any section. If I take Z, RC into Z. So RC into Z by EI. So this, you can see this is upwards. I'll just put a negative sign, multiplied by, if I take any section Z, so 1 multiplied by virtual moment 1 multiplied by Z, which is Z. So this dz, you can see here, this RC is at the end, so the Z here will be from 0 to 5. Okay, in this case, there was no force between 0 to 2, so we integrated from 2 to 5. Here, since our force we are already having, so we'll integrate from 0 to 5. Next, the moment for this column, so you can see here RC into Z. Okay, and here it will be 1 into 5. So here 5, here RC into Z means here Z is 5 meter. So I can say right here, instead of RC into Z, it is minus 5 RC. So 5 RC. Okay, this is the moment for this, multiplied by 5 virtual moment for this AB. So this is dz. Again, this is from 0 to 6. So calculating this is by EI. Okay, so minus RC z square, so ZQ by 3, EI I'll put 0 to 5, minus 5 5 is 25, RC by EI 0 to 6. Okay, so this is minus 125 by 3 EI RC minus 25 multiplied by 6, 150 RC by EI. So this gives me minus 575 RC by 3 EI. Okay, so we have found out deflection C in the secondary structure. So now for the flexibility method, so at the end we have already divided this into two parts. So we'll be using compatibility equation. So because we have divided this into two structure, that means the deflection at C in both the cases we can add it to find the deflection at C. So total, you can see here, because it's a support here, it should be 0, right? So I can write that deflection at C due to primary structure plus deflection at C due to secondary structure equal to 0. So this we found 1620 by EI. Okay, and this we have calculated 575, so minus 575 RC by EI, 3 EI. Okay, so this is equal to 0. So solving this equation, so RC we have found out 8.45 kilonewton. Okay, so once you know the RC, we can find out the shear force and bending moment diagram. So we have this 15 kilonewton, this is 2 meter, this is 3 meter, this is 6 meter, and we have now found out this as 8.45, right? So for this I can draw the shear force diagram as 8.45. so 8.45 till where the 15 kilonewton force is there, then 8.45 minus 15. Okay, so this is 6.55. Okay, this is okay. So this is our shear force diagram, and if you look at here, so we can have this as our axial force diagram. Okay, axial force diagram in which we have this 6.55 force for this member. Okay, this is, then if you are going to draw the bending moment diagram, so that also we can draw. We have this force reaction, we know this is 15 kilonewton force, we know this is 2 meter, this is 3 meter. So now 8.45 multiplied by 2 gives us the moment here, which is 8.45 multiplied 2 gives us 16.9. Okay, so this, under this we have this 16.9 value. Okay, this is 16.9. After that, if you want to find out what is the moment here at B, so moment at B is equal to 8.45 multiplied by 5 minus this 15 multiplied by 3. This gives us 2.75. Okay, so this 2.75, so 8.45 multiplied by 5 minus 15 multiplied by 3. So this gives a negative of 2.75. So somewhere here, let's put negative, so 2.75. Okay, this is negative. Now the same moment will come here. Okay, because there is, this will go to the support. It's 2.75. So this is your bending moment diagram. So So in this video we have analyzed a frame using flexibility method. Hope this video is useful to you. Thank you for watching.